So everybody ready to talk about some floppy disks? So I recognize some faces, but there's a lot of faces that I've never seen before. So just wanted to start off with a quick introduction of myself. For those of you that don't know me, my name is Paul Fiscarelli. I grew up with the color computer. My father got us one as a family Christmas present back in 1982. It was a 16K Coco 2. And even though it was for the family, it was something that quickly became my computer. So my brother's right here, he can probably attest to that. So my father had wanted to get us started in computing. He got subscriptions to T&D and Chromaset by Dave Larrequest. Anybody recognize that? He did, I think he was part of C-Load as well. And I would eagerly anticipate each new one each month. Naga is still one of my favorites. So, but anyways, I think I share kind of a common ground with most folks who are in the vintage scene. I am who I am today because of getting involved with the TRS-80 early on. I've always been doing stuff with computers. Went from Coco 2 to Coco 3 briefly, and then to the x86 world. And we grew up in upstate New York. I currently live in New Hampshire. Went to school, got my degree in engineering, upstate New York at RPI, computer and systems engineering. Spent the last 25 years working in IT and technology. Last 5 years, I've been over at MIT at their Lincoln Laboratory facility. Folks are familiar with that. It's focused on research around DoD type work. I work in a cybersecurity group, and I can't really tell you guys what I do, but what I can tell you is I get to play with a lot of really cool toys, and I work with some incredibly smart people, much smarter than I am, and it keeps me growing and challenged. So let's go ahead and get started. So what I wanted to cover today is talking about floppy disks, both the physical and the virtual images, disk images, some of the floppy disk tools that I've worked on for working with these disks, and also talking about wrapping up with floppy disk preservation and archiving. So even though this is focused around the color computer, there's bits and pieces that I think are going to be relevant to the entire community, and I think I've got a few different levels of tech in here, so hopefully there's pieces in here for everyone. So floppy disk controllers. So you guys remember these things, right? I'm sure a lot of you still use them. These were the two different form factors that were used by the color computer. We'll talk a little bit more in depth about these. Starting off with I'm not going to get into the hardware of this too much. Down at the bottom you can see there's a link. Mav, he does a really good YouTube channel, and he has an episode that he covers the floppy disk controllers in depth. So I'll stay away from the hardware side and focus more around the actual structure and software. But they started off with a 12-volt analog controller based on the Western Digital 1793 chip. It was 12 volt, and that controller will no longer work on anything but the early Coco 1s. Unless you have a multi-pack interface that supports 12 volts. They moved on to the next generation, which was a 5-volt PLL phase locked loop controller versus the analog, so much more reliable. It was based on the Fujitsu MB8877A, which is a clone of the Western Digital 1793, but it ran at 5 volts. So that was a big improvement for them. Then they went on to the 3129, and then they went into the 500 series, going all the way up to the 502. For folks that may not know, the 501 is probably the best one because that was the one that they used the gold-plated contacts on. It was the most reliable. They got a little bit cheaper with the 502.
Are those all double density controllers?
Yes, they're single-sided, double density, 35 track controllers. So, but definitely check out Mav's link there for a little bit more in depth on the hardware. So taking a look at the disk extended color basic format, the structure of the disk itself. So basically 35 tracks. One track is reserved for the FAT and directory structure. 18 sectors per track, 256 bytes per sector. The organization is in granules. There's 9 sectors per granule, so a total of 68 usable granules minus the directory structure. 2,304 bytes per granule gave you a total available storage of 161,280 bytes. The size of the actual disk of what it had for available storage was closer to about 213,000 bytes, but there's a lot of overhead in there, and we're going to talk a little bit about that. But if we take a look at this diagram over here, so basically the tracks are these circular rings, and then they're broken up into these sectors. This diagram is only showing 8 sectors here, whereas the Coco had 18 sectors per track. And one of the things you might notice here is the sectors aren't necessarily, the outer ring is going in order, but the inner ring is showing you what the logical sectors are. Logical sectors were the interleave or the stepping of the disk itself. And what they did that for was so that they could pick up more data on a rotation rather than waiting for the disk to completely spin around and have to wait to read another sector. This information pulled directly from the Color Computer Disk System operator manual and guide. So taking a look at more in depth on what's actually happening with the sectors and the overhead associated with it. These are the control bytes and what they actually contain. So what you have on each sector for timing purposes and for discrepancies with the hardware and the spinning of the motor, you had to have gaps and sinks on the disk, so it would know where to grab data. If everything was sequential, the timing would have to be extremely precise for you to pick up information. So what you have is you have these ID markers in here. You have the track numbers are indicated per sector. You also have CRC checks in there, which we'll get a little bit more into. The guide here from the Color Computer Disk System owner manual doesn't really give a full in-depth description on what these values are and where they are on the disk. So we'll talk a little bit more about that in depth as we go along here. So this is actually taken from the WD 1773 Western Digital white paper, or the data sheet for that chip, and this gives you a little bit more in depth as to what's happening here. So just to give you guys a little bit of background on this, why I got into this and why I even had to research this and figure out what was going on here. For those that may be familiar with the color computer community, we have a gentleman named Simon Jonassen who does a lot of really in-depth, basically mad assembly language coding, and he does demos and stuff like that. He reached out to me for some assistance. What we was ultimately looking to do was put this demo together that he could actually read data off a floppy disk and have music and animation happen in the background, which is really hard to do because the Coco has a non-maskable interrupt that you have to work around, and with that, you really don't have much time to do anything in between those read cycles. So Simon reached out to me. He said, "Hey, look, I'm trying to put this demo together, and I need a utility. I heard you had a utility." Which I did have, but it was completely different than what he needed. So it's about a year ago now, I quickly put together this utility that allowed him to do what he needed to do. And we'll get a little bit more in depth into that. So I had to learn all about what was going on with inside these sectors. So this here is an image of an actual disk that I was playing around with earlier, prepping for the demo. And this is an actual TRS-80 35-track disk. The software that I'm using to view this is HXC floppy emulator utility. So I used an imaging tool to grab an image of the disk, and then this is just a physical view or a image of the disk. So you can actually see each one of these are these sectors going around the disk. I grabbed both sides, even though there's only data on the one side. And what you're seeing here, this green area is where the data is. Then what you have is these gaps, which are what I talked about earlier. And then you have sync information in here. And you have a complete revolution that gives you your entire track. This gray area here is actually each track has gap and sync information in there as well. And we'll take a little bit closer look at that as we go in, more into the talk here. So talking about floppy disk virtual images for a minute here. So we have 5 different main flavors of virtual disk images that we use in the color computer community. The DSKs, which most people are familiar with, and all this really is it's a sequential array of sectors just mashed together, 256 byte sectors, just layered one on top of each other. As you can imagine, with a virtual disk image, you don't have to worry about timing of a rotational motor. You don't have to worry about the sync and the gap and all that. So that was an easy one for folks to come up with and start using. VDK is very similar to that, but they have a 12-byte file header on it. JVC is also very similar to that, but they only use a 4-byte file header. That's from Jeff Vavasor when he first came out with his emulator in the mid-90s. DMK, a lot of people will probably be familiar with that one because DMK is pretty much used ubiquitously throughout the community. Model 1, Model 2, Model 3, I believe Model 2, maybe not. Yeah. But David M. Keel put that one together. And then the latest iteration is the SDF, which is the stands for SD floppy format. And that was created by Darren Atkinson. Darren Atkinson is the one that created the Coco SDC. Many people in the color computer community have the SDC. They get them from Ed Snyder, but Ed collaborated with Darren to be able to sell those. So let's take a look here. So what I've got here is a DMK disk image, and we're taking a look at the track view. And basically each track is 6,400 bytes long, using an interleave of 1 to 7. On this particular one, I'm not sure why. I was probably just messing around with different timings of it. But what you see here is the actual track structure. And highlighting the IDAM pointers right here. The IDAM pointers are the ID field, and what you have is 2 bytes per sector. It's in little endian form, least significant byte first, most significant byte second, and this allows for a max of 64 sectors per track. So you can see here this AB80, it's kind of an eye chart here, it might be a little bit hard to see, would actually be 80AB, and the structure of that is the 80 being the most significant byte. That leading value of 8 is indicating try to remember. So it's a mask. You have to mask that off. Oh, I'm sorry. So the 8 is indicating that it's a double density disk. If it was 0, it would be a single density. AB is going to be the actual offset to the ID access mark, and that's going to be this FE value right here. And it starts from the very beginning of the track. So from this point here down to, this is our first address mark here. ID address mark is FE, would be AB bytes off. So we'll go down to the next one here. Then we have our gap, our first gap, which I have labeled here as gap 0. It's based on these 4 E values here. It's a length of 32 bytes, offset of 0 from the beginning of the sector. Next we have our sync, which are these 8 zeros here, offset at 33. We go down to our IDAM, which are these A1 values right here, these first 3 A1 values. And there's our access mark for our ID, which is our FE, and that's a single byte. Next, we have our track number, then we have our head number, then the sector number, and then finally we have our sector length. And this can be 0, 1, 2, or 3. 0 indicates it's a 128 byte sector. 1, which we have here, it's a 256 byte sector, all the way up to a full K for a 1024 byte sector. Then next we have our IDAM CRC. So this CRC, when I first started researching this, it was a bit hard to find information on it. What I ended up doing was ultimately checking out the Western Digital data sheet again to figure out what the calculation on that should be, and it took a bit of research to get that. But this first CRC here is actually calculated on these 8 bytes here. So it's the address mark, plus the prefix, plus all the track and sector information here. Then next, we have another gap. I have the zeros in there too, which are the sync. But that's your second gap there, labeled gap 1, and then sync 1 are the zeros after that. Then you have your data access mark, which are these next set of 3 A1 values here. And then that's your access mark there, which is your FB value. Then what follows is your 256 byte sector. And then the last thing is your sector CRC, which is basically calculating what the CRC is for the entire sector there. And again, trying to figure out what that CRC calculation should be was a little bit of a challenge. So how do you figure out a CRC? I mean, there's different calculators you can use for it and whatnot, but ultimately what you do is you have a byte stream value here, and you have to divide a polynomial divisor into it. And then once you get down to the end, you end up with a remainder, and that ends up being your checksum. So we have our polynomial value here, which is converted to a bit value here, but which one should we use? So again, referencing the WD 1773 data sheet, came up with this, and it provided this polynomial here. The CRC includes all information starting with the address mark up to the CRC characters. So what do I do with that polynomial? So what you end up doing is you end up using the coefficients on each of the polynomial to find the binary value. The easy translation for this is, so this would be our bit 0 value here is this 1, which correlates to this. The next one we have is this 5th power, which is this bit value 5 here. So we put a 1 in here. Anything that doesn't have a value or coefficient ends up being a 0. The next one up is 12. And then x to the 16, that's actually in the 17th bit place. That ends up rolling off on the final calculation. So we leave that off for the polynomial calculation. And that correlates to hex value of 1021. So that's what we would actually use for our divisor into our bit stream. And this ends up being a CRC16 CCIT false. It's very similar to X modem, but what you end up doing is your initial prefix is all 1s as opposed to all 0s like you have with an X modem. By any chances, anybody in the 6009 community recognize 1021? This is a little sidebar. What the opcode is for that? I'll let you guys look that one up. So there's a kind of an interesting tie there, but I'll let you guys look that one up. Taking a look at the SDF disk image, this again was created by Darren Atkinson to support specifically the Coco SDC. And I caught up with Darren on this. I asked him, why didn't he just use the DMK image? And the DMK, he said initially looked and worked well. Did you find it, George? Yeah. Yeah, so it's Long Branch Never, and basically Long Branch Never is my YouTube channel that I started I thought that was just kind of an interesting geeky tie there. So anyways, So getting back to this, the SDF disk image, I caught up with Darren and I was wondering why he didn't just use the DMK. And he had some great reasons behind it. He had started using it, but it wasn't going to quite do what he needed to do for his controller. So what he really wanted to do is maximize compatibility with non-standard disk formats, or basically copy protected disks. So anything that had interesting copy protection on it, where they had unformatted sectors or mixed mode sectors where some were 256 bytes, some were 1024, some were 512. He wanted something that was going to maximize the compatibility there. Another thing that was interesting is the controller that he used for that, the microcontroller, was the Atmega 328P, and that's limited to 2K of SRAM. So there's not a whole lot there to work with. What he was ultimately looking to do was to fit the entire track header into that 2K of SRAM. And the reason for that is the track data itself would require just over 6K of data, and by including the entire track header with sector ID information in that SRAM, he would limit the number of reads that he would have to use to access the actual disk image. So it's much more efficient track header, use of the track header, limiting the multiple reads. So this is very similar to the DMK format. As you can see, you have your gap and sync information in here. Here's your IDAM, and here's your CRC, here's your second gap. So it looks very similar. The key difference is this area up here. What he ended up doing was he's using 8 bytes for identifying what the sectors actually contain. So the first byte here is basically showing how many sectors are actually being consumed, or how many address or sector IDs are actually being used. The next 7 are they're reserved. He's not using them, but this here is giving you all your sector information, your track information, what the encoding is, and it's all being loaded at the very beginning of the track information. So that's all accessible by the microcontroller without having to do the multiple reads. And then the other thing that was really key with this is it also aligns with the 512 byte block size on an SD card, which makes it extremely efficient in that respect. So take a quick look at the floppy disk tools. And again, this is in reference to the custom utility that I put together for Simon Jonassen, where he put together his Gimme Gimes demo. And for folks that want to see that, you can just stop by my table. I won't run it here because it's a bit long, and I want to actually run it from a physical disk. But if you want to stop by my table at some point through the weekend, I'll show you that. So. Pause this for a second. There we go. See if it fits. Okay. So what this utility allows you to do is take a blank DMK disk image, drop it in there. Get a better view of it there. It tells you the size of the disk, how many tracks are there, what the current interleave is of that particular disk. And then you can take a look at it by track view or by sector view. So again, this is the track view, which I showed you earlier in the demonstration, in the talk. So if you want to take a look at it there. And then the other thing you can do, so just a little bit of background with it. Again, what Simon was looking to do was take a virtual disk image, convert it to a physical floppy so we could run the demo off a physical floppy, having it access data as quickly as possible. So what Simon was playing with was different interleaves, different ways of retrieving the data off the disk, being able to position sectors of data or blobs of data into whatever positions he wanted on the disk. So I'll take a file and I'll drop it into the left-hand pane here. And what that does is it basically loads it and it shows us our hex dump there. The name of the file being here, gal256.inc, and how long it is, how the size of it, and how many blobs it is. So from here, what I can do is I can go to tile mode, and that'll show me a different representation of the disk broken up into 256 byte sector blobs. So on the right-hand side, what we're looking at is the logical layout of the disk if you wanted to, and that's indicated by this here. So it goes from 1 to 14 to 9 to 4. So you can see it's actually skipping 6 sectors before it gets to sector 7. And that's why it's got an interleave of 1 to 6 or skip value of 6, because it's skipping 6. But you can easily just take a look at it in physical layout as well. So what he wanted to do is basically take this file here and put it where these blobs wherever he wanted on this disk image. So something much more unconventional than just doing a copy of the file to that disk image. So what I allowed him to do is you can basically take and pick a particular blob over here, and you can say, I want to put that one there, that one there, that one there, just random. And if you look, if you change the layout, you can see they're moving around because it's switching the physical and logical layout. But that's a bit cumbersome. So what he ended up doing was saying, all right, if we had a sector map on what the layout actually would be and basically set it up in a CSV format, could we stage it a little bit easier? So we can load the sector map. And this is basically just a series of comma separated values there that's showing where we want to lay out the data. We can pick the starting track. So I can go track 4, for instance, and then I hit stage, and it'll automatically populate all the blobs over there. So from there, we can hit commit, and it'll save the disk. I'll hit reset because I want them actually on 0. Stage, then commit, and then we can save our disk. So the other thing that it allows you to do is he wanted to play around with different interleaves. So I had it set up where you could pick which interleave you wanted to use. Some interleaves are nonsensical, they don't make any sense. That's why you don't see them all here. So if you did a 1-to-1, you can see they go in a sequential 1, 2, 3, 4, 1 to 2, 1 to 5, which is a skip value of 4, is standard disk extended color basic, and then you can change the interleave on the fly if you wanted to. So that's that. And just to show you what the results are. So I'll pull up this. This is the other disk utility that I was just talking about earlier, but we'll do launch it into MAME, and we'll do Cocoa 3 since it's a Cocoa 3 demo. So we'll see if audio comes through. Yeah, it's coming through a little bit. So it's accessing the disk. So as it's loading data from the disk, it's playing audio in the background and displaying it on the screen. So that's kind of the result of that. So, all right. So The next utility I was going to show you guys is this floppy disk tools, which I've been working on. So I originally started this in 2007, and I won't give you guys the full demo of it now. If you want to learn more about it, please stop by the table and I'll show you guys much more in depth. But I was looking for an easy way to work with virtual disk images, and being able to catalog them, being able to search through them. You know, I just found it where I was getting a lot of duplicates and such. So I wanted an easy way to manage the disk images and find information on them. So when you first start up the utility, you get presented with, well, I've created a catalog here, but you get presented with what your catalog of disk images looks like. And you can come through and you can basically highlight a particular disk image and it'll give you a preview of them. And you can see, various content here. And I just have random stuff here. And what's nice about this is you can come in and you can say, all right, I want to take a closer look at this file. You double click it and it'll give you file view. For most stuff, so it gives your hex view here. In this pane here, I'll blow this up a little bit. It'll attempt to do a disassembly of the binary. And the method I'm using on this is recursive traversal of the binary. So much like the program counter would step through the code trying to disassemble on the fly. And the reason why I did that was trying to get data to drop out from where the actual code is. So you actually get a more, it's a better representative of what the actual code looks like. Here's an Explorer view, which gives you a little bit more in-depth view of the disk itself and the files. So you can highlight files, and you can get, this is what the Cocoa character set looks like. You get your sector map here. You can come in and you can hit edit, and you can edit content on the disk. So, and we won't commit that, but you can do, basically a sector edit here. Down here at the granule table, you can actually click on a granule and it'll take you immediately there. You can go to directories. It also functions as a nice launcher for any of the content with the various emulators. And of course, it's showing on the screen here. Let's see. So yeah, that'll launch into the emulator, and it supports the three major emulators. So if you wanted to do a launch into MAME and any of its variants, you can do it through there. VCC, XOR as well, which is another popular one. Some of the other things you can do with it is if you wanted to search for particular text, it'll bring you and do a search for you, and it'll provide clickable links. So if you want to click on that, it'll bring you right to the binary itself. You can search by hex. There's tools in here for finding duplicate disks, duplicate files, and whatnot. It's got a settings menu, so you can change any of the various settings in here. So yeah, there's a lot going on here. I actually did an alpha release of this at the last Cocoa Fest, so back in May timeframe. So we've got a few people in the community testing it. If you want to check it out and play around with it, by all means, let me know and get you a copy of it. So.
Just that runs under Windows?
So it runs under Windows right now, and what I've been trying to do is get it to work under Mono for Linux. So when I originally started this, like I said, it was in 2007, and one of the things I did not want to do is spend a whole lot of time building a UI. So I put Visual Studio to the test and was able to basically do drag and drop UI out of the box. Had quite a bit of Visual Studio experience at that point, so I just ran with it. So I may end up doing, a new version of it that's, cross-platform compatible. I'm not sure what that would look like, but if we can get it running under Mono, then that might be a big win for the Linux folks. Tried a little bit with Wine on Mac and haven't had too much luck with it yet, but we'll give it some shot. I know some people in the community are looking to play around with it, and at some point I'll open up the source for it so others can start playing with it. So, actually, so we talked about that. All right, so the last piece that I wanted to talk to you guys about is talking about floppy disk archiving. And there's modern hardware available for doing this. So the three big ones right now are the SuperCard Pro by CBM Stuff. They do a lot of Commodore stuff. There's the CryoFlux controller and Catweasel MK4 Plus. Have any of you played around with these or heard of these? Anybody use them? Okay. So I have a Catweasel. It's primarily for the Amiga. It was developed around the Amiga. And I had limited success with it. And I still have it in a system. I just haven't used it in a while. About a year or so ago, I came across the CryoFlux, and I really like that one right now. Oh, it's magnifying. So the CryoFlux was developed by the Software Preservation Society, and what their goal was, what their mission was to be able to archive and just grab data off of these aging floppy disks. The nice thing about this is it reads the flux transitions off the disk itself, so at a very fine granular bit level. The interpretation layer is abstracted from it. You can use the interpretation layer on the fly. What they originally started with was creating these stream files, which was just a raw magnetic flux dump of the disk. They end up being very large files, but the nice thing about that is if you have disks that are aging and you may only have one shot at reading data off of that, you do a stream file of it, and it's an exact, as close as possible, magnetic duplication of that disk, and you can reference that for any of the interpretation type data transitions that you want to try on it, and you never have to touch the floppy again. It's USB based. It does support Linux, Mac, and Windows, and people that use them have had success with 8-inch, 5 1/4, 3 1/2, and 3-inch. So as you might notice, I do have what looks like TRS-80 floppy disk hard drive or floppy drive up here. However, the difference is I've got a USB cable plugged into it, and that's because I have my CryoFlux right in the controller or right in the housing itself. So what I'm going to do is we can come back to questions, give you guys just kind of a live demo of that. So there are command line tools for it, which are phenomenal, but some people have layered GUIs over the top. And this particular one is Java based, which is kind of, it does the job, but. So make that a little bit bigger. So the first thing I need to do is just make sure that the CryoFlux is connected and can be seen. Let's try quick calibrate. right, you might not be able to hear it, but what it's doing is the head is stroking on the path right now. And what it's trying to do is find out what the maximum number of tracks are available on this particular drive. So it's actually calibrating the drive. And it came up, you can see down on the bottom that it's looks like it's 83, which is just an odd number, but it's just what the stroke is on that particular head. And you'll find different values for different drives. So I'll grab a disk here. And this is just an old Rainbow on disk that I have here. Throw that in the drive. And you have a lot of different, great. It's dual screens. So you have a whole lot of different parameters that you can set around what you try to read off the disk. The CryoFlux stream is, again, the raw dump of the disk image. You can do FM sector-based images, MFM. There's a lot of support for Commodore and Amiga, Apple, and these are out of the box. You can basically do your own. So I have one that I created for the Coco. I've got a MFM that I did and a Coco Stream, and it's just basically modifying the values over here. So I'll grab the Coco MFM, and basically it's just side 0, which is a single-sided disk, DSK extension. We have 256 byte sectors, and our track distance is 40 tracks. Cancel. Just type in a disk name. Hit start, and I'll start reading the disk. Oops, I did the wrong one. I'm doing a Coco Stream file, which would do the entire, well, actually, while I'm doing this, is it going to show? So what you can look at on the fly is what the histogram looks like for the data that it's pulling off or the bits that it's pulling off. The scatter plot's probably the most useful. So what you're seeing here, this is just noise. It's not reading anything, and it's pretty much picking that up on the second side. Where you do see data is when you see these 3 tiers here. And what these 3 tiers are, it's actually showing you what the flux reversals actually look like as it's going, the disk head is going across the disk. This first line here, this lower line, is the main one where it's grabbing data, and then what you're seeing above that are second and third harmonics from the reads as the head's going across and doing the reversals. So I'm going to stop this because it takes probably about 2 minutes or so to do a full read, and it's doing both sides when it really doesn't have to do both sides. I'll show you in a second. So I'll change it to Coco MFM sector image. Let's start. And here you can see that it's going track by track. And the reason why it's skipping over tracks is because I have a quad density drive in here, and it's reading double density, so it's skipping those other tracks. So when you're doing this one here, you're not seeing any histogram or scatter data because I've got the interpretation happening on the fly. So what it's actually doing is converting the magnetic transitions off the disk into that data interpretation, which is converting it to actual sectors. And there it is, it's done. And you guys can't see it, but it created that disk image for me right there. If I double click on that disk image, it popped open my utility, and there's our disk content. So it's that easy to create a disk. Yeah, and if you wanted to, you could script it with command line and just pop in disks all day long to be able to retrieve that data. The nice thing about this, again, because it's doing it at a magnetic flux level, even disks that you think that you can't read, that you're putting into a drive that you're getting I/O errors on, this is going to grab every single microscopic piece of bit data that it can off the disk. You can actually use tools to go in and piece together pieces of data. So a good use case for this, last year after Tandy Assembly 2018, I had the good fortunate opportunity to meet a woman. She had a Craigslist posting for some Tandy gear that she was selling. She actually had 3 pallets of it. And she was up in Burlington, Vermont, and I'm like, I'll do anything to get my hands on that. It wasn't so much the gear. I mean, yeah, the gear is important, but you can get gear from anywhere. I could tell that she had a lot of different boxes of discs and data and that sort of thing. And I really wanted to get my hands on that to find out what was going on with that. Well, she ended up meeting me about halfway. I met her up in New Hampshire. And turns out her husband is a gentleman by the name of Bob Hudson. Probably don't recognize the name, but he had a little company called Frostbite Software based out of Burlington, Vermont. And he put together a color Lisp interpreter for the color computer. And I started digging through the material, and I found a bunch of references to it, but not much else. She contacted me a few weeks later, said she found some more stuff, had some disk images. So I started looking at disks, and there was a bunch of I/O errors. Started playing around with the CryoFlux, found some of his source code. It wasn't all there, but started piecing that together. And lo and behold, she contacted me a few weeks after that, found a very early version hard copy of his source code as well. So one of the things that I'm working on is piecing that all back together. CryoFlux was huge in being able to read that disk data that I wouldn't otherwise been able to read it. So it's really neat. So what I'm hoping is, folks in the community will, start looking through their disks, and even if they're getting I/O errors, the best thing is, if you have doubts, don't mess with the disk, because you can do harm, and irreparable harm. Get them into the hands of somebody that can, use a CryoFlux. I believe Ira offers that service. I'm not sure what he has for hardware, but I know that he is of the same mindset. Don't mess with the disks. Get them the disks. You can get them clean. You can transfer them into sleeves if the sleeves are damaged, and there's opportunity to read data off of them. So that's why I wanted to show you guys the CryoFlux today. But it's the tool that I've been using to do archive and preservation. So with that, any questions, guys?
When you were pulling down one of the drop downs, there was something that said like Big 5 format or something.
Was that on the CryoFlux software?
I think so. I was just wondering if you had any idea what that means. Is that like some copy protection scheme?
Yeah.
It might be. So I have used this for getting copies of discs that I own that are OEM from the hardware, or from the vendors themselves. Dave Dye's products, the Sundog Systems. Some of these guys that use pretty heavy-duty copy protection, and being able to archive them. I was going to show a live demo here, but I reached out to the authors for permission, and I didn't hear back from any. So I didn't want to do that without their permission, basically showing that there's a tool out there that can get by their copy protection. So, but it's something that I'm still learning. I don't know all the ins and outs of it, but I've found it to be an extremely powerful tool. Big 5 sector image. Yeah, so the CBM, what's that, the Commodore Business machines? So, yeah, so that might be what that is there.
So it's not for their TRS-80 stuff?
I don't think so. I mean, but if it's for CBM, I'm sure it could be adapted for the TRS-80. So
Ira actually has a cat. He's off the camera. It's an ancient DOS machine.
okay.
And one question: have you ever gotten into that whole business of faking discs or dealing with mold or solvent on to try it?
So what I've done is I've had some that get mold and mildew on them, and what I do is use a little bit of alcohol, diluted alcohol with them, and just gently dab them to try to get the mold off of there, and I've had some success with it. So, it's unfortunate that, these are physical medium that does have a life expectancy or shelf life. And, if they're not treated with the utmost care, they get to the point. Ian was showing earlier how, some heads will, just shred the discs, and it's really kind of sad. But along those lines, talking about what may still be out there, the Apple community just had their Kansas Fest in July over the summer, and the name escapes me, but there's a new product that they have called Applesauce, and what it does is they put a IR pair in for the timing with I think there's maybe a Hall effect sensor or something that they use for getting accurate timings of the disk, and they have a similar utility that they're retrofitting their Apple II floppy disks with, and they've had tremendous success with it, doing a very similar technique. And at Kansas Fest, they had like these sessions where people were just bringing in their disks, and you would think in the Apple community, as large as it is, that they probably got everything cataloged, and they have all this data, and there's nothing else to be found. Apparently, they found literally hundreds and hundreds of pieces of data and programs and things that they never even knew existed that were just lying around on floppies. And I'd like to see similar movement for the TRS-80 for the Tandy folks, and not just Color Computer, but anybody that's, again, it can pretty much do any. It's not just Color Computer. It's not compatible. So the disk itself is a double density, but the quad density, it will read the double density or the single density. Write back is a little bit more challenging, obviously, with that, but I have gotten good success with it. So two things. One, because it was a drive that I had laying around that actually worked well with the CryoFlux, it won't work with all drives. You'll find drives that it just, it doesn't like, and if you go to their site, it'll show you which drives are actually the best suited for the hardware. But the other thing too is for IBM stuff or anything that I might have that's quad density that I want to try to retrieve as well. So it's not just for the Color Computer, even though I have it in a Color Computer case, but can be used with multiple disk types. And
Is that from the T2K? That's right.
And so, no, the one I have in there, it's I believe it's a Mitsubishi. This is this is an IBM drive, or from an IBM computer.
Oh, okay.
Yeah. So.
The correct drive is good if you're not sure what format the disk is, because if you see duplicated tracks, it's a 40 track drive, 32 tracks, but it's an 80 track. Okay. Disk.
Any other questions?
The CryoFlex roller, right?
Yep. So it'll write. I believe it'll do FM. It definitely does MFM. Where it has its best success is the Amiga. There's an Amiga format that it does really well. But I've found that the best luck that I've had, especially if I'm doing something that's copy protected, is just doing a stream file and then writing the stream file back. The challenge with it is because it's not, there's no syncing, there's no gap information in there, there's no anything, it's just raw magnetic bits. Getting the timing and the sync right can be a little challenging, but most of the time I've been pretty lucky with it, especially with drives that are in pretty good shape. So.
Will it work with multiple drives?
Yeah. So.
5 or 3.
So I don't have it in there right now. I took it out before I came, but right down here I have a 3.5-inch drive, so it does support multiple disks, and you can basically on the fly through this particular interface is cancel. You pick the drive and you have drive 0 or drive 1, or you can pull it right from a stream file. So the other thing that's nice about this is the stream file the raw files that it creates, you can use with other utilities. So I can use with that HXC floppy emulator and write that directly back to a DMK image if I wanted to, which is nice because that'll handle some more, it's more flexible with what it handles for output. Any other questions? Thank you.